Okay, YouTube, in my last couple of videos, we've explored the basic behavior of exponential growth functions. That is to say, we were looking at functions that were of the form y equals a times some base value to the x power and their basic shape of their graphs, which, by the way, recall that they have an asymptote on the x-axis. They go through the point 0, comma a. They tend to do this. And that they grow exponentially or decay exponentially depending upon whether b is a proper fraction. But here's our basic exponential growth function. What I want to do in this video is I want to expand our definition or understanding of y equals a times b to the x to include two more values, and these values are going to be h and k. And I do want to point this out. These are the very same h and k that you deal with when you talk about, say, parabolas in vertex form, or when you talk about absolute value graphs even. You know, we say a times the absolute value of x minus h plus k. And so what these do are they influence how our graph shifts. Okay, so we're going to make a little note here. We say that the value of the letter h will control the amount of horizontal shift, or what we say is horizontal translation in math, of our graph of y equals a times b to the x. So here I make a little note. H is lying to us. It seems backwards from what it is, and we'll take a look at that kind of pattern here in a second. And we say that this value of k right here, this is going to control our vertical translation. Okay, vertical translation, whereas h is horizontal translation. Okay, so the good news is we will practice at least and get the hang of graphing these very quickly because they have the same asymptote, the same intercept every time, and we can, get their basic shape from the characteristics of a and b. Okay, but for the most part, this will be the same thing except for we're going to shift our graph. So you'll notice here that when I say let's go make a graph of this, down here I say you're going to start by sketching y equals a times b to the x, and we're going to ignore h and k altogether, and then we'll apply those later. So what I want to kind of do here is explore h and k, and what I did was I made this graph right here, and this is the graph of y equals a times b to the x, and now I put plus h on purpose, and we talk about y, but plus k here. And so I've got my table of values here. You can see 0, 1s on our graph, 1, 2, 2, 4. The idea here is that with our h and k values, what do they do to our basic graph? I have put in a base value of 2 for our b and an a value of 1. So we notice that that a value tells me that I hit my y-axis at 1. There's an asymptote on the x-axis here. And our base value of 2, if we were to plug in, say, 1 into our function here, we get 1 times 2 to the 1, we get 2. The idea is that when we start messing around with h and k, when my h value gets, let me do this here, h. It's kind of hard to tell. We'll go with k first here. We'll make h 0. When you mess around with a k value, there we go. All you're really doing is you're taking your graph and you're translating it, up and down, up and down, up and down. It'll be a little bit easier to see now because I can click off these points right here, and you'll see it shifting left and right, but this is kind of like shifting it right, shift it left. It looks like it's peeling it up and peeling it down with those points, but shift it right when my h value is negative and shift it left when my h value is positive. Okay, so what I can tell you is it shifts exactly that many units up, down, left, and right respectively, or respectively left, right, up, down. So you'll notice here that when k is 5, if I add 5 in my k, my whole graph, its asymptote was the x-axis before. Now the asymptote is up at a height of 5 because everything about this graph shifts up 5. So what we're going to do essentially is follow my instructions over here, but we're going to sketch 3 graphs here, just sketch them, and state their domain and range just by using our basic knowledge of y equals a times b to the x and then translating it. So when I say let's make a graph of y equals 3 times 2 to the x minus 1 power minus 4, then state the domain and range, the very first thing I want to do is I want to do this. I want to identify what are our a and b values here. So I see that my a is this and my b is this. So if I'm going to sketch this graph, let's talk about a few things that we know about it already. It's got an asymptote on the x-axis. Okay. The next thing I know is that on the y-axis it hits at a height of 3. So we say 0, 3 is on my graph. We should label this. We should. 0, 3. Okay. I should also, for good measure, always not just plug in 0, but also plug in 1 to get another point on our graph. So I say y times equals 3 times 2 to the first, that'd be 1, 6. So we'd say that this is at a height of 6 right here. And so this graph right here would look like this. And this is the graph, everybody. And I should label this 1, 6, follow my own advice. This is the graph of y equals 3 times 2 to the x. So the idea is that since I know what this looks like, then I should know what y equals 3 times 2 to the x is if I have an h value. In this case, I'm going to write this down. H is positive 1. It's lying. It's backwards from what we see. And then we say k is negative 4. This is telling the truth. We say lies, tells the truth. So the only difference between these two graphs should be that this new graph, and I'll put it in green or something like that here, should be the same as the original graph, but everybody gets shifted 1 to the right and down 4. So we're going to take every point here, we're going to go 1 to the right, 1, 2, 3, 4, down 4. So this is the point now. This is the point 1 comma negative 1. And then we'll take this 1 to the right, 1 to the right, down 4. And it'll be here. And this will be the point, well, it was 1, 6. So now it's 1 to the right of that is 2. And then down 4 from 6 would be 2. So this is the point 2, 2. The other thing to keep in mind is that if everybody shifted down 4, this thing that was at y equals 0, this asymptote, is now at y equals negative 4 also. So we're going to shift it down 4. So the 2 points that we have initially, we're just going to shift them, and then we're going to shift our asymptote if necessary. And you could see that we get this graph right here that looks like this. So this would be the same graph. The green one is the same graph as the original graph. This is y equals 3 times 2 to the x, but minus 1, and then that minus 4. Okay, so when we talk about the domain and range of this, let's go ahead and bury those really quickly here. I'm keen on doing that. We say domain and range. The domain is always going to be all reals. We say all real numbers. And the reason why is because any x value you put into an exponential function, you get a y value back. Your graph goes left to right forever and ever. But as far as the range of this goes, I noticed that it goes down to a height at lowest of negative 4. This is kind of on the y-axis, the barrier of how low it goes, and then it just goes up forever and ever and ever. So we're going to write its domain or its range as this. We are going to say y is greater than negative 4, and then we'll leave it at that. We say all y values greater than negative 4. So now these last two graphs, let's take a look at those. We say y equals, and you know what, it seems that I pasted the same one here, so good, there's only one more graph to look at. Let's take a look at this graph here. We say graph the function y equals negative 3 times 6 to the x plus 2 minus 2, then identify domain, range, and asymptote of the function. We'll do the same thing here we did in the last one, which is start by just kind of throwing the graph of this together right here. So if I were to say let's make a graph of this, I would say let's start by finding a couple of points. We'll plug in 0 and 1 for our x values. When I plug in 0, we should just get negative 3 for the point. Negative 3. Okay, that's a property of these graphs. And when we plug in 1, we get 6 to the 1 is 1 times the negative 3. This is negative 18. Okay, so what this tells me is that it hits the y-axis, the parent function does at least there, and then the next point would be at 1, negative 18. It's like, you know, we're going to exaggerate here. 1, negative 18. We could say that this is 0, comma, negative 3. We could even go backwards. We could say if I plugged in a negative 1, we would get this, by the way. Y equals negative 3 times 6 to the negative 1 is negative 3 times 1 over 6 to the positive 1. So we get negative 3, 6, or negative a half. So I guess we could say that this is also on the graph right there. This is negative 1, comma, negative a half. I'll throw 3 points on here. But we have an asymptote that is the x-axis, and we have this graph that comes in, and it is growing very quickly here. Right there, and we say this is the graph of y equals negative 3 times 6 to the x. Okay, so now that we have this growth function listed, we say that this graph has an h value of actually negative 2 and a k value of negative 2. We can see that these are evident here. Here's our k, and our h is hanging out with x. So we would say that this entire graph is going to shift left 2, down 2. So this point here was negative 1, comma, negative a half. We're going to go left 2. So negative 3, comma, negative 2 and a half. So we have negative 3, negative 2.5, forgive the big writing there. And we say take this left 2 down 2. So we're going to be at negative 2, comma, negative 5. And if you took this left 2 down 2, it's down here somewhere. But we say I also have to take the asymptote down 2. So here's this new asymptote, and it's going to be y equals negative 2. You could quickly see how that's actually always going to be the same as whatever the k value is, because whatever you pick up or move down your graph, you know, that height that you shifted up or down, you're going to be shifting the asymptote with that. So here's our new graph. We say y equals negative 3 times 6 to the x. It would be plus 2 minus 2. So here's this graph in blue. And by the way, again, with the domain, we say all reals. It's going to go left and right forever and ever. And the range, talking about the range, we would say that y is always less than, I would say, -2, a height of -2 right here. Cheers.